Okay, back again. We're going to continue with parallel circuits and calculating resistance and that kind of stuff, but we're not going to do the last part of the series that I'm doing. We're actually going to just do a side trip into the past by looking at this issue of Popular Electronics from October 1966. So this is quite an old little magazine. It's still in reasonably good condition, but the interesting thing is she's listening to her record player there, which is quite good. What if I got on my fingers? I should really have cleaned that off. Hold on a second. I don't know what that is. I think it's the felt tip pen marks. Didn't clean my fingernails though. Sorry about that. But that's just the way things go. But anyway, today we're going to look at this voltage divider quiz. So this is in the magazine. Hopefully it will show up on the camera and you can see what it is. They kind of have all these things here where they've got, they want to find out which two, so what it has here is it has little points labelled on it, A, B, C, D, E, F, and G, and H. And these are the points that will have a voltage potential, well, a voltage difference from ground. Well, they have, I don't know what the right term is, but they want to find out the differences in voltage potential, or differences in voltage or whatever, between different nodes. So what they basically, they want you to say like, well, where's something with a difference of 0 volts? What two nodes have a difference of 0 volts? And what two nodes have a difference of 2? What node has two nodes have a difference of 2 volts, and so on and so on and so on down the page. I don't know if I've explained that. It's not that important, but you'll kind of see what I mean at the end of it. Why I say it's not that important, I know that's the whole point of the question, but I'm going to clean my nails off camera, are going to just calculate the total resistances and currents of the circuit, which we need to do to actually answer the question. So we will answer the question at the end, but it's the journey that's going to matter today. So anyway, we're going to start. So this one here says, it starts off, so the important thing is there's a battery over here, and the battery has 30 volts, and this is the positive terminal here. It's coming up here, going through here, back down to here, to back into B, which is like the negative terminal or the 0 volts point. So this is the 30 volts at the top and 0 volts at the bottom. When I say 30 volts, I mean it's 30 volts from the lowest point. So everything voltage is, just to reiterate, because I've sort of said it all very strange at the beginning, voltage is always like measured as between 2 points. So there's always a voltage difference. It's not like this point actually has a voltage in some sort of absolute terms. It only has a voltage relative, for example, to the lowest point, which is B. So I might say that D has a voltage of 20 volts or something, but I'm meaning there's a difference of 20 volts between D and B. Anyway, let's start with the first one. So here it's got 4 ohms. There's a resistor of 4 ohms. They used the zigzag line style. 3 ohms and 8 ohms. So we want to find the best way to do this, answer this question, is we can find the voltage differences between each of the nodes and B. Then we're all set to go to answer the rest of the questions. But first we'll go here. So I've written it down here. That's a 4, that's a 3, that's an 8. And I've done it square style, and here's 30 volts. So this is just that one little line there, written out in hard to read felt tip pen. So we know a couple of things from yesterday, or from the last video about resistance, is that resistances in series, they add up. So we can find out what the total resistance is across this line here. This part of the layout, this part of the circuit, and we can do that just by adding them together. So we've got 4 here, 3 here, and 8 here. So the total resistance equals 4 plus 3 plus 8, which is 15 ohms. So the total resistance across here is 15 ohms. And we know from Ohm's law, which is V equals IR, which you can rearrange to I equals V divided by R. So I just move the R underneath the V. Which makes sense, right? So then I can say, well, what is the current that's going through all of these little segments? through this whole section here. So not through the whole circuit, but just through this section here. And we know this from I equals V over R. We know what V is. The voltage difference is 30 volts. So the difference between here and here is 30 volts. And we know that the total resistance is 15 ohms. So the answer is 30 divided by 15, which is 2 amps. So there's 2 amps of current going through here, which is a lot of current to be pushing through there. So they're probably going to get quite warm. You're probably going to want the bigger. Sorry, I've got one over here. You want one of the bigger resistors for that one. But this is not like a realistic thing, because I don't know how often you get resistors in 3 and 4 ohms. But you can make them by putting them in parallel, as we have discussed yesterday. But we know from this here, so if V equals IR, we can also work out for each ohm how much voltage are we dropping. Well, we know what the current is. The current is 2 amps, and we're saying how much are we going to drop for 1 ohm of resistance. So in this case here, the voltage drop will be V equals 2 times 1, V equals IR, which is 2 volts. So that's just saying, in this case here, for every ohm of resistance, we're dropping 2 volts as we go through here. So I went through and I calculated the total resistance, then I calculated the current going through the whole thing, and I know the current is the same all the way through, because you don't want things to bunch up, or they won't bunch up, they can't. And so from that I can then work out, well, for each of these little, each ohm of resistance that I'm encountering, how many volts do I have to use. So it all works out. You can just also get this way, of course, that there's 13 volts and there's 15 ohms, and so you've got to have 2 volts per ohm. It's just another way of saying it, probably the easiest way. And so given that, if you're at 30 volts and then you use up you go through 4 ohms, how much voltage does that cost you? Well, it's 4 times 2, which is 8. So we used 8 volts to get past this resistor. So what voltage are we at now? Well, we're 30 minus 8, which is 22. So we're down here, and then we've got 3 ohms to get through here, and so we're going to need 6 volts for that. So 3 times 2 is 6. So if we were at 22 now, and then we're going to put another 6 volts, so it's 22 minus 6 will get us down to 16. So this point here will be the 16 volt point, and then to get down to the bottom, we're going to need 8. So 8 times 2 is 16, so we can check our answer here. And so we know that we have to go through 6 ohms, and that matches up. So when we go through the 6 ohm resistor, we get down to 0, which is where we're supposed to be. So we know that it all adds up. So that's how we do one line. So applying that logic, I have a little picture. So that was the first side. So we're redrawing it slightly. So this is 30 volts at the top. Hope this is in the frame. And this is my 4, 3, 8 resistors that I did from before. The next one along is actually 9, 5, and 1. And 9 plus 5 plus 1 is also 15 ohms. So that makes things easy. So we can go back to our previous logic, and we now know that each ohm costs us 2 volts to get through. So we've got, again here, we've got 9. So I'm going to go through, and I don't know how well this is going to work, but I made these little labels. So I know I just discussed this, that C was 22 and D is 16 volts. So we've kind of got the answers to that one. I wish I had some. Where did I put my blue tack? Disappeared. Rotter. Okay. And so now we've got E. So we're starting at 30 and we've got 9 ohms to get through. We're going to use up 9 times 2 volts, so we're going to get down, so we're going from 30 minus 18, so 9 times 2 is 18, we're going to get down to 12 volts there, and then we've got to get down another 5 ohms, which is going to cost us 10, so we're going to get down to 2 volts at this point here, and this is very messily done, but hopefully it comes out okay in the thing. People are like, why can't you just use like computers, because it takes too long. Alright, and over here, handily, you're not going to believe this. Oops, and I've moved everything. I knew I should have had something to hold them in place. You can just hold it in your head. It's real easy. I think. I don't know. Don't. Alright. Well, you can if you want. Memorize these numbers. Just keep repeating them over and over again. C equals 22, D equals 16, E equals 12, F equals 2. Just keep saying it. And anyway, we're over to here. And these, as I was saying, 7 plus 6 is 13 plus 2, which is 15. So this is also 15 ohms. So again, we can say each ohm costs us 2 volts. And so we go from 30 volts plus 2 times 2 is 4. So we're going to go down to 26. So 30 minus 4 is 26. And then that's another 7. So that's 14 volts it's going to cost us. So 26 minus 14 is 12. And then we're down to there. And 12 times 6, 2 times 6 is 12. So we can check our answer. In this case here, I missed out this one. 1 times 2 is 2. So that works out. Hopefully this won't fall off. And so if we were going to answer these questions, the interesting one here is where it says 0 volts difference. And there are actually 2 points on here that have the same voltage level. So there's actually 0 voltage potential difference between these 2 points here, which means you could put a little wire across here and it wouldn't change the circuit because there's no voltage difference, so no current will flow through that wire, which is kind of like an interesting thing if you haven't quite got it so far. So these are the same voltage potential, whatever the word is. It's not voltage, it's electric potential, I think. It's like I'm terrible. I'm teaching electronics and I can't remember the exact term. That's what I mean. The whole point of this is that you get inspired and then you go read the book and then you know all the right terms. Please don't inundate the comment section with the correct term is, because I don't care. I will get it myself in the end. Anyway, so this is actually, I'm really kind of afraid when I get like more viewers, so I'm going to get all these comments and I have to look at them and reply to them, and I'm like, oh, I don't know. I'm sure it'll be fine if that ever happens, which it might not. So anyway, we've solved the first one. There's only one case where there are 2 things which are of the same value, and that's the only way you can get 0, unless you count the bottom bits which aren't included. And this one here is 2. So we're saying where there's a 2 volt difference. Well, we've got this case here, 2 to B. So in this case, the answer to that one would be F to B is the answer for 2. You can't really see the question. So 4, apparently there's a whole. We'll just do 4. So for 4, there's apparently 4 different cases where there's a voltage difference of 4 volts. So we'll just finish that up. So obviously there's the D to E. So that's 16 volts, and this is 12 volts. So if we had a little wire there, that would be dropping. Well, if we measured the difference in this, so there's a voltage difference of 4 volts between these things. If you put a wire in there, it wouldn't actually be the same thing. It would muck everything up because they're different. But there is a voltage difference of 4 volts there, and then we've got the other 12. So that's 2. So D and E and D and H is 2 of the answers, and we've got 2 more to find. So we've got the 22 and 26. So 26 and 22. So G and C, or C and G is the answer. Or G to C, sorry. We should probably do it so that it goes in the same direction each time. So in this case, D to E, D to H, G to C. And we have to find one last one. And because it's upside down, I'm probably going to miss it. What's 22 to 4? I feel like I'm missing something here, that's for sure. Are there actually? Hold on, where's the last one? Should be answers in the comments. Oh wait, of course, there is going to be one more, and I know where it is. It's from A to G. So A is at 30 volts, and then we go to G, and we have a voltage drop of 4 volts. There, so we've got A to G, G to D, C to H, and C to F. So that's the answer for those first things, and we did it. So that was good work. And we had I have one last piece of paper to show you. So going back, because we've got basically a series circuit here. So we've gone through and we worked out what the total resistance is for all 3 of these, and all 3 of these, and all 3 of these. It turns out it's 15 ohms, sorry, for each of these. If you wanted to work out what the total resistance is for this whole section here, So this is a parallel circuit, parallel layout. In that case, we have 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So each of these are 15 ohms. So we've got 1 over 15 plus 1 over 15 plus 1 over 15, right, which equals 3 over 15, which equals 1 over 5. So RT, because RT is at the bottom here, was the reciprocal of that, so that flipped over, and so that is 5 ohms. And that makes perfect sense, right? If you've got 15 to go through here, 15 to go here, but 15 and 15 to go through here, but you've got 3 different paths to go through, it's going to be 1/3 the resistance. If that kind of does make sense. But it's definitely a lot lower than going just through one path, right? If it's 15 to go through here, but I can send them down, I can send my little troops down this one as well. I'm going to get twice as many troops through, and if I can send them down this one, I'm going to get 3 times as many troops through. And the other way of saying that, of course, is that I know that the total current going through all of these. So the other thing to remember is that the total current going through here is going to be the current going down this part, and the current going through here, plus the current going through here. And so in each case here, it's 15 ohms, 30 volts, 2 amps go through here, 2 amps go through here, 2 amps go through here. So the total current is 6 amps. So there's 6 amps going through the whole circuit. We know that there's 30 volts going through it. So 30 volts equals 6 times the resistance. So in that case, the resistance, just doing some basic algebra, the resistance equals 30 divided by 6, which is 5. So the same answer, and that's how you get that. So I was going to go through actually and explain why you get this 1 over RT thing by doing something like this. Maybe I'll do it, but hopefully you can leave that as an exercise for yourself. So yeah, thanks for that, and that was just a bit of fun, and I guess we should have a quick look at what else is in this magazine. Lots of strange, somewhat older circuits and bits and pieces. So we will actually look at some magazines from the ages and see if we can do some of the circuits in them. Perhaps not the ones from the 60s, because most of these are like with the valves and stuff. Well, there's a one for making, it looks like it's making some kind of sound, or it's amplifying something. So we can play around with some of these. Maybe not this magazine first time. But look at that, it's got electric guitars and record players and all these things. And look at that, lots of radio things, and look, even one of those kind of tape players, which is pretty neat. And whatever that is. So yes, all right. So I don't think you make something that actually tells you the time by speaking it. I think it's actually just a radio that's saying the clock thing that they have on the radio, probably back in the 60s. But anyway, thanks for watching, and I'll catch you next time.